Assalamualaikum. My name is Azib Shami. We are from Group 1 and this is our presentation for our subsonic aerial vehicle design. We are tasked in designing and evaluating an unmanned aerial vehicle or UAV to carry the task of cloud seeding operations. These are the members of our group: Ahmed Azwa, Aino Zafira Fatini, Daniel Rahmat, Irfan Hazwan and Azib Shahmi. For the airfoil selection process, three different airfoils are chosen based on the literature review conducted for this project. The chosen airfoils are E423, S1223, and Wortmann FX63137. These airfoils are then analyzed through the software XFLR5 based on parameters set and calculated through the estimation of cruising Reynolds number. The estimation is done through the specifications set for the wing dimension, with the assumption of a rectangular wing, which are based on articles and journals researched for this project. The data received from the XFLR5 are then graphically visualized through 6 different graphs: lift coefficient against angle of attack, drag coefficient against angle of attack, lift to drag ratio against angle of attack, drag polar, pitching moment with respect to the aerodynamic center, and pressure coefficient distribution at angle of attack in cruise. The data is then analyzed and evaluated through the airfoil selection criteria, in which the airfoil Wortmann FX63137 scored the highest and the airfoil E423 scored the lowest.
Assalamualaikum, my name is Ainur Zafira Fatini binti Ayub. So we proceed with the concept generation to determine the airfoil size, shape and position of each part based on the design requirements and estimated wing area. So here are our 4 concepts that we have considered and their characteristics. This process was aided by a bar chart in order to determine the best concept for the desired airfoil. We have set UTM drone as our datum, as it is also studied on the UAV for cloud seeding. As we can see, concept 1 is the preferred choice due to its high number of positive attributes. It has a longer wingspan which provides better lift and endurance. Besides, the fuselage-mounted wing and tail reduce the drag, weight and complexity, while the swept back wing enhances the stability. So here are our final concept selection, which is concept 1. With its fuselage-mounted tail configuration, it offers advantages of reduced weight and complexity compared to the other concept's tail configurations. Additionally, the backward sweep of the winglet improves directional stability, facilitating easier control. This concept also has the potential to reduce drag and increase lift, further enhancing the performance of the UAV. And the record wing tip concept improves aspect ratio and reduces drag caused by lift.
Hi, my name is Azwa and I will present the wing design of our mini project. We have utilized a proper engineering design process to carefully select the best wing design for our project. We use a bar chart to evaluate and compare the different design criteria for our wing. This helps to make an informed decision based on the advantages and disadvantages of each design option. The first design criteria we considered was the number of wings. We compared monoplane, biplane and triplane design. After careful evaluation, we conclude that the monoplane design had several advantages over the other options. It excelled in terms of weight, cost effectiveness, speed and efficiency. Moving on to the next design criteria, we compared different vertical wing location, low, mid and high wing design. Our analysis indicates that the high wing design scored the highest based on our criteria. It had advantages in terms of payload interference as the wing was located above the fuselage, eliminating any interference issue. It also did not require dihedral assistance because of the fuselage itself acted as a pendulum for the wing location. Moreover, the minimal attachment points reduced construction and maintenance costs. After careful consideration for the high lift device, we found that slotted flaps were the most favorable type. They allow the highest maximum lift coefficient while generating less drag compared to split flap. This was due to the delay in flow separation on the airfoil. The slot created by the functionality of the flap also increased the surface area of the wing. Lastly, we considered the sweep and dihedral angle for our wing design. We chose a dihedral wing design over an hedral design. The dihedral wing design had advantages that outweighed the alternatives. So this is the wing that we designed for this mini project. We designed the main wing with 30-degree sweep angle. These are the parameters for each of section of the main wing. At the first section, it is a flat wing with 0 degree. The wing is cranked dihedral for the next wing section with 3 degree at the second section, 15 degree for the third, and 30 degree at the last section.
For the performance evaluation, first the lift coefficient versus angle of attack graph. The graph trend shows that the lift coefficient is proportional to angle of attack. When angle of attack increase, the lift coefficient is increased. For this graph, the lift curve slope indicate a lift coefficient at CL 1.6 at angle attack of 3 degrees. Comparing this value with the requirement needed, which is CL, the coefficient lift is 1.4306 for the design, we conclude that the CL obtained from the lift curve slope graph is larger than the requirement needed for the CL. Next, the drag coefficient versus angle of attack. The slope is increasing where the trend is increasing where the drag coefficient is lower at the lower angle of attack, but it increase rapidly in higher angle of attack. For the L over D versus angle of attack graph, the value shows that increasing trend and start to decrease after reaching at the maximum point, where the maximum point is at the 12.7 value of L over D at the angle of attack of -1. For the pitching moment versus angle of attack graph, the value of the pitching moment are showing it is decreasing as the angle of attack is increasing, where this graph shows that the stability of the design.
Okay, now for the design optimization and performance enhancement part, we stated that wingspan that we use is equal to 4 meter, and in this part we calculated the mean geometric chord and taper ratio. Okay, for the mean geometric chord, we got 0.1583 meter while the taper ratio is 0.625. Okay, the next part we calculated the range and we got 300 kilometer. And the last part, uh, we calculated the minimization of stalling speed and we got 13.06672 meter per second. Okay, now we will go to the discussion part. In this discussion, concept 1 was chosen as the final concept based on the future evaluation. Concept 1 featured a fuselage mounted wing and tail, reducing the coefficient and weight while simplifying the design. Its wetback wing configuration improved the stability and increased aircraft velocities by delaying the impact of airflow shifts. The incorporation of neck wingtips further enhanced the wing's aspiration and reduced drag caused by lift. As we conducted analysis using VSP Aero, monoplane was chosen over multi-wing planes due to their streamlined design, which enable faster flight and higher altitude capabilities. The first section of the wing has a tapered shape with an aspect ratio of approximately 10, which enabling a high lift coefficient. It also has a moderate sweep angle of 29.97 degree and angle of attack 1.26 degree dihedral. The second section, known as a crank dihedral wing, is angled upward, while the third section has a higher angle of 15 degree, which increasing the lift coefficient of the aircraft. The last section of the wing is angled at 30 degree. Okay, the CL against angle of attack graph predicted by VSP Aero showed the decreasing lift coefficient was 1.6 at angle of attack 3 degree, while the value of CLC2 was 0.619. As CLC actual was equal to or greater than CLC2, it was determined that the airfoil met the requirement criteria. The lift curve slope graph indicated that the lift coefficient obtained was 1.6 at an angle of attack of 3 degrees, surpassing the required value of 1.47 of UAV design. This confirmed that the airfoil's lift production met the necessary criteria, ensuring sufficient lift for takeoff, maneuverability, and stability during the UAV's operation.